us go to the concepts of today. And in this lecture 2, I've written the just the subtitle that of what we are going to learn today, that is called the mass spectrum. And before even just I got the mass spectrums, I would like just to do the correction of homework 1, which I gave you in lecture 1. Okay, homework 1. So make sure that you go there. I left the questions and this is the correction. So the questions was asking you that what the meaning of the word. Let me just look at questions, please. So the questions was asking you what the meanings of the word recorded mass. What the meaning of the word, yes. What the meaning of the term that we are using mass spectrometer, that we call it yes. Define the terms isotope ratio mass spectrometry. I believe you did it. So let me do correction for you so I can start a today lecture. We say that in the isotope ratio mass spectrometry, the isotope mass, okay, the isotope mass spectrometry mean that this is IRMS. In short, we say that is a specialized use of mass spectrometer, use of mass spectrometer, use the mass of the spectrum, the specialized use of mass is a specialized use of mass spectrometer to determine so this is to determine, okay, to determine the relative abundance of isotopes. Relative abundance of isotope, relative abundance of isotopes in a given sample. So look, if you are right, that is that the response. If you are not right, take that as correction. Okay, so let us continue with the today questions, and I would like just to start with these questions that define. So let us define the term mass spectrum. Say with me, define mass spectrum. What is mass spectrum? That's the question that we have. What is the meaning of the mass spectrum? What does it mean? When you say that the mass spectrum, what does it mean? So that's the question that we have on the playground. Mass spectrum. Not mass spectrometer, it is called the mass spectrum. Very interesting concept. It's a very unique concept, and it's very interesting for you. So I found two definitions of this term, and in plural we call it we call it mass spectrum. The plural word of spectrum is mass spectrum. At the plural. So we say that the definition, we say that the mass spectrum is a plot of the relative abundance abundance of the relative abundance of the relative abundance, okay, of the relative abundance of ions forming a beam as function of the mass to charge ratio. I taught you in the first lecture, mass to charge ratio values. So this is the one of the issues. So this is the plot. It's not an story, or it's not an history. It's a plot of relative abundance of 40 of ions forming what? These ions, they form beams, are the function of mass to charge ratio. Very interesting. So it's a plot, it's a graphical representation of relative abundance in the y-axis, because this is two-dimensional, okay, in the y-axis. And the mass to the charge ratio is as the what? As mass to the charge ratio as x-axis in two-dimensional plane. Or some of the references define that this 10 mass spectrum as this one. Is a plot of what? Is a plot of relative is a plot of relative abundances of 40 of ions forming a scheme. I talked about stream 1, stream 2, stream 3 in lecture 1. Okay, scheme visors. Okay, visors, they are mass to charge ratio. So in bracket we say mass to charge ratio. Okay, mass to charge ratio or values. Mass to charge values, mass to charge ratios, values, mass to charge ratio. So I think that, let me correct, mass to charge ratio values. So this ratio is right at mass over charge values. Okay, and then we say that he obtained from an instrument, obtained from values, these values are obtained from an instrument called what? From mass spectrum. Mass spectrum. So these are the two definitions that I found. I found many, but I chose this. So this again say that is a plot of relative abundances of 40 of ions forming a scheme visors their mass to the charge ratio values obtained from what? Mass spectrometer. So obtained from mass spectrometer. What do these two definitions mean? It means that if you remember that the diagrams of mass spectrometry, especially that in the deflection region. So this is the diagrams of mass spectrometer. Yes, I remind you what we covered in lecture 1 because I love you so much. Okay, so this is magnet. So these are the two bars of 40 of magnets. So, and this is the highly speedy accelerated ions which have been which is leaving the acceleration chamber. And then when it reaches here, because we have dotted lines, then what is going to happen is we are going to, this ion is going to experience what? Deflection. So, and this deflection depends on what? Mass to the charge ratio. So for this one, this we call it in chemistry stream what? This we call it in chemistry stream 1. Okay, and then the middle, again, we call it in chemistry stream 2. And then the last one, this we call it in chemistry stream 3. Okay, so these two ions, these three ions, for example, if an element are three isotopes, they are going to not the recording section. So what is going to happen? So this is a plot. Mass spectrum is a plot of 40 of relative abundance, right? Relative abundance, whether in percentage or it's not in percentage, against or at the functions of either sort, Pfizer's mass to charge ratio. So mass to charge ratio, in short, we just write like this way. So then, how do you represent this stream? Very good questions. So this is the way that, if example, that this is the stream 1, and this is the stream 2, and this is the stream 3, for instance. So these streams, they have different mass to the charge ratio. So this is, for example, that mass to the charge ratio 1, mass to the charge ratio 2, mass to the charge ratio 3. But remember that because these are the isotopes, so it means that the elements or are the isotopes of the same elements, so it means that their charge will be the same. So, but here we have peaks. So these peaks are what are the relative abundance in percentage, or relative abundance, or we call them intensities. So this is the relative abundance or what or intensity. So this is the meanings, or this is what we call the this is figure, okay, figure 120, okay, 122. Then we call it the mass spectrum. So this is what we call mass spectrum, not mass spectrometer, mass spectrum. So don't confuse, remember that, not this in ions. A spectrometer, the word spectrometer is not equal to the word spectrum, right? So this is the spectrum, this is the part of 40 of mass spectrometer. In case you have any questions, don't hesitate yourself, ask in the comment section. So again, I have another question. Why the mass spectrometer? So we have to explain why the mass spectrometer, is known as what? Fingerprint, we call it why is it fingerprint of an element? So this is a very interesting question. Okay? Why is it known as the fingerprint of an element? So I want to give you the response. Can you take a minute to think before I give you the response? Why do you think that the mass spectrometer, the one I taught you in lecture 1, and give you all the details, why this is called like a fingerprint? You know the fingerprints? Fingerprints are like this, right? Why is it called like a fingerprint? Okay? So the response is very simple, because just take your fingers and then suppose that this is the palm of your hand, and then you have stream 1, you have stream 2, you have stream 3, right? So you have 3 streams for the an elements which have 3 isotopes. So if, for example, that is an element has 2 isotopes, then you have 2 streams. So that's the meaning. So it means that because it's playing, it is displaying the result like the fingerprints. It means the streams of an atom or of an element are like the fingers of my hand. So that's the concept. So we say that the answer is, it is known, what is it? Mass spectrometer. It is known as fingerprint because when it is used to analyze different elements. Different elements. Okay? Different elements. Then it produces what? Produces the mass spectrum. The mass spectrum. Called the spectra or spectrum. The mass spectra in plural because more than one spectra. The mass spectra, okay, in form of what? Because it's a forming a streams, okay? Mass spectra of streams of ions. Streams of 40 of ions. So these are the reasons why it is called a fingerprint. Is it interesting? Yes, it is interesting. So now we can call the mass spectrometer, it's a fingerprint of an element. Interesting. Very interesting in advanced chemistry. So then our interest right now, I would like just to let us go, because I told you that in this lecture we teaching you the results of mass spectrometer. How do we interpret it? So let us go to a little part which is called, or a little subtitle called the interpretation. Interpretation of 40 of peaks in the mass spectrometer. In the mass spectrometer. How do you interpret these peaks in the mass spectrometer? That's the question that we have. How do we interpret them in the mass spectrometer? So these are the peaks. Peak number 1 for the first isotope, peak number 2 for the second isotope, peak number 3 for the third isotopes. What are the meaning? Because this is a graphical results from the mass spectrometer. So what do they mean? That's the question right now. So that's why that you want to know, and I have to teach you how we interpret it. Okay? So sometimes the questions, you may be asking the questions in the exams, or even can ask yourself, what is the number? What is the number of peaks, okay, of peaks in the mass spectrum? In the mass spectrum represents that's the question that we have. Okay, so we say that this depends on what it has been analyzed in the mass spectrometer. So we say that, so what is the number of peaks? So we say that in the mass spectrums represents. So we say that the representation depends on the input of 40 of mass spectrometer. In case you find that I'm going too fast, you can pause the video, you can write, and then so you can continue. Okay? Input of mass spectrometer. What does it mean? It means the input might be, so we say that the input or the ions or the input might be, okay, might be what? An element such as sodium, or a molecule, or a compound. So depends. Okay? So let us start with Roman R. So the interpretations, that is Roman R. Okay? For an element, if the input, for example, introduced in the mass spectrometer, is an element. For an element, we say that the number of peaks. The number of peaks represents the number of isotopes. The number of isotopes. This is very important concept. So we say that the number of peaks represent the number of isotopes. In case if we say that if an element is an input or a sample introduced into the mass spectrometer is an element, then this number of peaks represents the number of isotopes. So for example, in this plot we have how many peaks? 1, 2, 3. So how many isotopes are there? 3 isotopes. That's the meaning. Interesting? Fantastic? Yeah, it's true. It's fantastic. Okay, good. So simply in few words, we say that the number of peaks in the mass spectrometer, right, is equal to the number of what? Of isotopes. Number of isotopes. That to say, if an element results 2 peaks, then it has 2 isotopes. Isotopes. Etc. etc. Okay. So then the representation or the structure now of the plot for an element, which is actually what you have to cover, this representing intensity, relative abundance. Sometimes we can represent the peaks as what in y-axis with the parameter or physical quantity known as intensity or relative abundance. So relative abundance, and this relative abundance is expressed in percentage. And then here we have mass to charge ratio, which I've mentioned frequently. So for example, if an element has 2 peaks, then we say that is the way that we present. Here we have mass to the charge ratio 1, and then this is mass 2 to the charge ratio 2. And then here in the y-axis, we might have intensity 1, or we call it percentile 1, relative abundance 1. And then here we have again another peak. This one presents as the intensity 2, or we call it relative abundance, sorry, not percentile, relative abundance, but not in percentage. So for example, that in that graph, so this we call it is figure 1.3. So we say that the mass spectrum of of an element, which is what? Uncombined. In bracket we write that uncombined. Uncombined, because for the molecule we have combined the elements. Okay? So that's the case and that's the concept. So because I told you, in case that you have any question concerning about the interpretation, then you may ask in the comment section. But I would like us to give you the homework. The homework is this. So this is homework 2. Make sure that you do. Okay? And I would like us to give you 2 questions. So question 1, what does number of peaks of a molecule represent the question. And then the second question for your homework, we said that what does number of peaks from the mass spectrometer okay, of what? Of a compound represent. What does it represent? And the question. So make sure that you do those two questions, and I believe that you'll come back with very good answers and a way of practicing yourself on how to explaining chemistry phenomena. Okay? In case you have any question, please don't hesitate to yourself to ask in the comment section. Okay, good. So then now you have a fundamental, or you have a clear concept. You understand what the meanings of the concept known as mass spectrum. So I would like now to take you into the serious part that I've been waiting to teach you for a long time. And this serious part, we call it in chemistry, how we calculate the relative molecular mass of by using the mass spectrums of mass spectrometer. So before we go to this subject, let me remind you, you learned the concept of relative atomic mass firstly when you were in O-level studies. And now let me remind you the meanings of it, because we are going to spend the rest of the entire of this lecture, of this session, of this period, on discussing it. So relative, say with me, a relative atomic mass. Again, a relative atomic mass. I know that you know. Possibly you forgot it. What does it mean? How do you find? What does it represent? I will spend few minutes to teach you, to remind you. Okay? To remind you. Because I know that you are, historically, you were very good in chemistry, in O-level chemistry. What is the meaning, or define what the meaning of the word, what are relative atomic mass? This is the nectar question. This is advanced certificate secondary education examination nectar question. So don't take it easy. Okay, there are many definitions of this concept, but let me give you one. We say that relative atomic mass is the average, is a weighted average, the weighted average of the relative isotopic mass relative isotopic mass, okay, relative isotopic mass, in abbreviations we call it RIM, okay, of the isotopes of what? Of the isotopes of the element, relative to 1 to the 1/12 mass of carbon 12 isotope, whose mass is carbon 12 isotope. So this is one of the definition of the term relative atomic mass. Is a weighted average. So this is an average of what? Of relative isotopic mass. It means that we take relative, remember this is relative abundance, isotopic mass. So it's a weighted average. What the meanings of average? Average means we take sum of our number of items, sum of the items of a number of items, sum of the statistical data, if it is group D or ungroup D, sum of them, and then for ungroup data it is sum of the statistical data of a number of statistical data. That the meanings of 40 of the word average. So it's weighted because again it does not involve the summing and the divisions only. It's weighted because it involves 3 operations. We have multiplications, we have addition, we have division. That's the meanings of the word weighted. Understand it and bear it in your mind. It's a revelation. Okay, so relative isotopic mass. So this is the weighted average of relative isotopic mass of the isotopes or 40 of the element relative to. It means we do compare with 1/12 mass of carbon 12 what isotope. So the abbreviations is RAN, and then the unit we can use, we have 2 types of units, atomic mass unit, and in some cases that we might use some other units which are actually very interesting. Some of example that we call the gram per mole. But the SI unit, it has some other units. Okay? So we say that the unity of relative atomic mass of an element is atomic mass unit. Excuse me when I remember that I say gram per mole. Gram per mole, that the unity of 40 molar mass. So the unity of relative atomic mass is called the atomic mass unit. In abbreviation called AMU. Very interesting unity in nuclear physics, and in physics or even in chemistry we can cover it later. Okay, good. So then, I don't want to waste much of your time. Allow Sir Olenjolai to take you now into the calculation, the subtitle or the concepts of calculations of 40 of relative atomic mass. So calculations of relative atomic mass. How do we calculate? So we say that when a sample of an element is introduced in the mass spectrometer. Then the mass spectrometer produce what I told you, what will it produce? Produce mass spectrum. Mass spectrum. And this mass spectrum and the peaks of mass spectra, as we say, represents what represents the number of isotopes. The number 40 of isotopes. Right? Of isotopes. Okay? So we say that the plot of mass spectra